Good morning, students. Today we'll have 4.5 worked example. An element delta L equal to delta xi means the length of the element is delta L, which is along I vector, that is x-axis, is placed at the origin and carries a large current of 10 ampere, I equal 10 ampere, as shown in the figure. What is the magnetic field on the y-axis at a distance of 0.5 meter? The distance of 0.5 meter as shown in the diagram, delta x equal to 1 centimeter. The diagram is shown in the NCERT textbook. Please go through it. Dear students, this is one of the simple example. I had a small length, that length is delta L, which is written as delta xi vector. Means this delta L is part of a length which is carrying some current, that is 10 ampere current. Delta x means since it is along x-axis, I can take it as delta equal to delta xi vector. It is along x-axis. If current is flowing here on the right side of this wire, I will have a simple wire. Think the wire is here. If current is I, right side it is cross, this is a plane and it is a dot. So since right side is cross here and left side it is dot, the magnetic field here is a dot. And what it means, magnetic field dot indicates it is coming out. This is y-axis. This is dot indicates magnetic field. It is out of plane. Magnetic field is coming out of the plane. Of course, if I say it as x-axis, this as y-axis, z-axis will be normal to it. Means magnetic field is along z-axis. Yes, let me cross check. What are the formulas? This is a wire concept. You have I, L cross B. Magnetic field force or magnetic field is given by a simple analysis. How to calculate that magnetic field and a force concept? Let me write a simple formula. Magnetic field dB is given by I dl cross R. The distance is everything simple. As I said, I'm interested in a magnetic field at a point. The distance is 0.5. Now you have a small current and you have a length. It is called current element. So let me use this formula. So you have magnetic field at a point P at a distance 0.5 meter according to Biot-Savart's law is given by mu 0 divided by 4 pi into I dl divided by r square. And of course, this IDL cross everything is your sine theta. This is at a 90-degree x-axis and dot. So sine theta becomes, sine of 90 becomes 1. That is taken up. Now this is your vector. Now this dl cross r, dl is along x-axis, this r is along y-axis. It gives you a magnetic field along z-axis. So it is going to be I vector cross j vector, which is going to be next finally a k vector, magnetic field on k vector. The moment I substitute these values, which are this equation 1, it is written as dB mu 0 upon 4 pi is equal to 10 raised to minus 7. I is 10 ampere. DL is 1 centimeter. 1 centimeter means 1 into 10 raised to minus 2. In the denominator, you have r square. R is, of course, distance is 0.5 meter square, right? 0.5 whole square. The simplification gives you dB. dB is equal to minus 7. It becomes minus 2. Minus 1 becomes 10 is here. 10 into 10 raised to minus 9. In the denominator, 0.5. 10 raised to minus 1 becomes minus 2. 25. It becomes 25 into minus 2. Minus 2 becomes plus 2. So it becomes dB, this magnetic field, is equivalent to 10 upon 25 into minus 9 plus 2. So finally you have 1 upon or 5 2 ja, 5 5 ja, 2 by 5 into 10 raised to minus 7. This 2 by 5 is typically, you can write it as 20 by 5 into 10 raised to minus 8, or you can write finally dV, which is equivalent to, if I write it here, 20 by 5 is 4 into 10 raised to minus 8 Tesla. The answer is very simple answer. It comes out to be magnetic field at a point here, dV equal to mu 0.4 pi ideal. Substitute all the values, you'll end up with 4 into 10 raised to minus 8 Tesla. This gives you a right hand thumb rule. This is called magnetic field right hand thumb rule. Very simple. Think you have a loop. The magnetic field looks like anti-clockwise, and it is anti-clockwise. And this is a magnetic field at the center. It looks like the current, this is current I, whereas this is the direction of magnetic field. And it is something like, look at it, when you have a circular loop, if current is going anti-clockwise, the direction of magnetic field is upward. If current is going clockwise, the direction of magnetic field is downward. So anti-clockwise current, when you look from the top, the direction is towards you. Anti-clockwise means just unscrew it. When you unscrew, the screw is coming towards you. When you give a clockwise rotation, the screw is moving away from you. That's the same direction. Anti-clockwise current, magnetic field is towards you. If it is a clockwise, it is anti-clockwise current in the diagram, so magnetic field is upward. If current is in the clockwise direction, magnetic field is downward. So this is a small analysis. Now, this is again a magnetic field curve. This is a magnetic field curve. I need to draw it, yes. Now, similarly, you have one more curve. And similarly, you have a curve. So, which is again, typically we will show in this fashion. It is in the fashion of a loop. Yes. So similarly, you have a magnetic field. Similarly, you have a magnetic field. Similarly, you have a magnetic field, which is in the form of loop. Always they give rise to a circular loops. Yes, this was a small analysis. This is your magnetic loops. They are closed paths. And the arrow marks are very standard. They enter, yes, they come out, and magnetic field. This is all magnetic field lines. They enter from the bottom, they come out. And here you can see, yes. This is again your loop. This is again a current, and this all is your magnetic field. And what is this symbol? That this arrow mark indicates your curl, indicates this anti-clockwise indicates when you have a thumb, you have fingers, curl the fingers. When it is like this, you just go on curling them, you just go on turning them. When you curl it, the direction is anti-clockwise. Curling like this, it starts curling. When you curl the fingers, the direction is upward. This is direction of magnetic field. It is called right hand thumb rule, whereas the curled fingers will give you the direction of a current. Current is I, and this is a magnetic field. When I talk about a right hand thumb rule, this is a direction of a magnetic field, and this is a loop. Loop means a wire which carries a current I. If current is anti-clockwise, your magnetic field is upward. You can see, and all the arrow marks are upward. It starts from the bottom. The thumb indicates the direction of the magnetic field. And what is this finger first? Finger indicates, the finger shows when your fingers are curled. Curl means turned in the direction of the current. it gives you a thumb. Thumb is the direction of magnetic field. Similarly, if the fingers are curled in a clockwise, anti-clockwise means if the fingers are curled anti-clockwise, we will get a magnetic field upward. If the fingers are curled clockwise, that is downward, magnetic field is downward. That is called right hand thumb rule. We will go with next one, 4.6. A straight wire carrying current of 12 ampere is bent into a semicircular arc of radius 2 centimeter as shown in the figure. Yes. Consider the magnetic field B at the center of the arc. Means you need to calculate what is the magnetic field at the center of the arc. There are three cases. A, what is the magnetic field due to the straight segments? B, in what way the contribution to magnetic field from the semicircle differs from that of the circular loop, and in what way does it resemble? Would your answer be different if the wire were bent into a semicircular arc of same radius but in the opposite way as shown in the figure? There are three sub-questions. We need to address all of them. This being one of the simple numerical where I need to calculate what is the magnetic field at the center of the loop. Now this is a straight part and also this is also straight part, same current. Current enters and it travels in this path. It is called a semicircle arc. It is called semicircle arc. So what is the contribution of this straight part when current is flowing here? I can take it as I dl. This dl is called a straight part. When I take this formula, you remember we had a magnetic field dB due to this element, current element. What is the magnetic field here? Magnetic field here, it is called as dB, call it as small dB. This is equal to mu 0 divided by 4 pi I dl, whereas this is called displacement vector from here to here. The current gets over. The direction of this ideal, this dl means this wire, and this is one and the same. You can put it cross divided by r cube. R cube means this r cube I am talking. Yes. When I talk about this whole angle is 0. Since theta is 0, this whole dB becomes 0. Means the contribution due to this straight part or this straight part at the center of the loop, the first part, the question A is asking, this is A answer. The first part of the question is, what is the magnetic field at the center of this semicircular loop due to the straight part? This is a straight part and this is a straight part. It is 0 because the angle theta is 0. Because the angle between these two, dl and r are parallel. dl cross, they both are parallel. Hence the angle theta is 0. Hence this whole magnetic field becomes 0 here. Now when I take the second part, B part, you can call it as half of the circle. It is called semicircle. For a circle, this is a formula. Magnetic field due to circle is mu 0.2 I upon r. For semicircle, half of this. What is half of this? You write it as B by 2. If this is a magnetic field at the center of a circle of radius r or small r, mu 0 I upon 2r, I can make it half of it. It becomes finally mu 0 divided by 4 I by r. This gives me a simple value. Mu 0 upon 4 indicates mu 0 is 4 pi 10 raised to minus 7. Mu 0 is written as 4 pi minus 7 divided by 4. I is 12 ampere. Radius is 2 centimeter. Write it 2 10 raised to minus 2 becomes plus 2. So this is very simple. 4 nullifies, 2 1 ja, 2 6 ja. It is 6 into 3.14. You have minus 2, you have plus 2. It becomes minus 5. And 6 3 ja 18. It is roughly, you can take it as close to 20. 20 into minus 5 Tesla. The magnetic field is 2 into 2.0, or I can write here at the center B is equivalent to this value. It can be written as 2.0 10 raised to minus 4 Tesla. And this is a magnetic field which is at the center. And look at this analysis. and here the current is flowing. All the contributions, since it is here, as I said, when you have wire, here it is a cross, here it is a dot. Here the magnetic field at the center is a cross. The direction of magnetic field is into the plane. It is called into the plane, into plane of a paper. It is coming out of plane, Means because of a current here, this contribution to the magnetic field is zero, this contribution to the magnetic field is zero. Whereas from here, whenever current starts flowing in the semicircular part, all this cross means magnetic field, all the magnetic field due to this element, you go on chopping this whole semicircle into small parts. So all will get add up and it becomes half of the circle magnetic field, because if you have a circle, the magnetic field is given by B equal to mu 0.2 I upon R. Since it's semicircle, all the individual contributions becomes B by 2. B by 2 once you calculate becomes 220 into minus 5, or you can say 2 into minus 4 Tesla. That is going to be a small magnetic field which is at the center, and its direction is into the plane I have written. This is going to be one of the interesting part. If you consider similarly another wire which is bent in this fashion, if the contribution to the center due to the straight part is 0, again this straight part is 0, whereas the curved part, again the contribution is there, the magnitude is given by B by 2. It is B means magnetic field due to a circular loop, which is called B, which comes out to be this formula. You will get double this, 4 into minus 4. So half of that is 2 into minus 4 Tesla, and dot indicates the direction of magnetic field here is coming. Yes, look at this. This is clockwise, and this is, of course, this is a different part. This is clockwise and this is anti-clockwise. For anti-clockwise, it is a dot in the center, and you will get a cross here, dot here. And for this, you can notice if it is cross here, it will be dot outside. Everywhere, this is cross because it is clockwise. When you have wire, it is entering like this thumb rule. It enters cross, it comes out dot. Here, the current is going in this fashion like this. Here it is a dot and here it is a cross. This is a magnetic field.